Okay, we're going to continue on here. Chapters 14 still, part 2, I think, essentially. So in this sort of second part of chapter 14, we really got into the idea of the common ion effect. And again, essentially the idea here is if you have a weak acid or a weak base, it will normally dissociate into its ions a little bit. And if you do have some type of common ion, like we talked about, I think with this guy here, if we added some sodium acetate, so if we dumped a little sodium acetate in there, this is going to be a source of sodium ions and acetate ions. And again, that'll be essentially like adding more of the acetate to this equilibrium that's going to be set up by the weak acid. Le Chatelier's principle is going to have it shift away from that side. And what it will essentially do is keep the weak acid or the weak base basically from dissociating completely like it would normally do without the presence of that common ion. The result of that really in terms of sort of pH, as we talked about, is obviously our H plus concentrations over here on the right-hand side. And since pH is equal to negative log of the H plus concentration, by it shifting the equilibrium really away from the H plus side in terms of the pH, what we will see is the concentration of H plus will go down, and we will actually see the pH of that solution sort of be higher in comparison to, say, the weak acid by itself or the weak base by itself. Now, as we talked about, obviously in this case here, we wouldn't necessarily get like a basic pH or anything like that, but it would be higher in comparison to the acidic pH there that we would see with just the acetic acid by itself. This sort of idea of common ion effect really is what the situation occurs when we have buffers. And buffers, as we talked about, are solutions that can resist changes in the pH when you add more acid or base to them. So what we're talking about here is the idea that we can have a solution that will be able to really maintain its pH of where it started at without really having really big swings in pH when we add acid or base to it. The way that a buffer is able to really work is based on what it is really made out of. And also important thing that we talked about as well is that a buffer is not necessarily a neutral solution. You can obviously have a buffer at any pH that you make. It just means whatever pH it's at, it will basically be able to maintain that pH when you add acid or base. Also, we talked about the idea that it will actually move pH, so it won't really just stay stuck right there at that pH. If you add acid or base to a buffer, you will see the pH go up or down a little bit. And we won't see, though, again, the big swings in pH and really big changes in pH when you add acid or bases. And really the reason for that is what it's made up of. It's made up of one of two combinations, either a weak acid and the salt of its conjugate base, which is really still your Bronsted-Lowry definition, basically two things that are related to each other by a difference of an H plus. Or you could have a buffer that's made up of a weak base and the salt of its conjugate acid. One thing that you cannot make a buffer out of is a strong acid or a strong base. So a buffer itself, and you're like, hey, this is my buffer solution, cannot be made up solely of a strong acid or a strong base as being part of the buffer. And that is because a strong acid and strong base will 100% break apart. You will have no way to keep both parts of the buffer in the solution at the same time. And you basically will just have either the base part or the acid part. You won't have both parts. The reason why a buffer works well with a weak acid or weak base is because those weak acids or weak bases will set up the equilibrium, like our acetic acid example here. When that's in the solution, the acetic acid, because it's a weak acid, will be able to set up that equilibrium. And basically, as we talked about last time, keep both the base part of the buffer and the acid part of the buffer in the solution to begin with. And by adding really the salt of its conjugate base, like the sodium acetate in this example, what you're really doing is sort of beefing up the base part of the buffer, so there's a good amount of it in the solution to sort of begin with. And again, with a strong acid or a strong base, there's no way, again, to keep both of those things in the solution at the same time. Ultimately, the way a buffer works, as we talked about, is it prevents the formation of free H plus or free OH minus when you add additional acid or base to your solution. So it prevents that formation of free H plus or free OH minus when you add additional acid or base to it. And as we saw last time, if you were to add acid or base to a non-buffer situation, like we talked about, which was something like water, if we just added our HCl to water, it would, as we know, completely break apart into H plus and Cl minus. And what it would do is produce a lot of free H plus into that solution right away. And that is going to have a pretty drastic effect on the pH because the amount of H pluses just went up a lot and the pH will change a lot because of that. Same thing if we added our sodium hydroxide, for example, to water, it's going to make Na plus and OH minus. Once again, it's actually in this case going to produce a lot of OH minus really quickly. So in that case, you would have a lot of hydroxide into the solution really, really quick. And that's going to cause a very big jump in the pH in sort of the upwards direction. Remember that the concentration of H plus and OH minus are tied to one another. So as one goes up, the other goes down and vice versa. And in this case, this is why we see a really big jump in pH when we add acid or base to a non-buffer situation. Basically, you're just dumping in H pluses and OH minuses. Yeah. So it probably, in most cases, you might make your buffer out of an amphoteric type substance. But usually in this case, we would be looking more at like a kind of you need like a strong acid or strong base to it. It would perhaps react in a way, based on, if it's going to be more acidic or basic. But in a lot of cases, a lot of buffers are actually made out of those things, like HCO3 minus and stuff like that. You can make a buffer out of this. Other questions? So what happens when we do add these things to our buffer system? Again, because we do have basically both parts. So if we do look at that acetic acid, sodium acetate buffer, and a reminder as well, as we talked about, the sodium here is really not doing much. So it's not really even part of the buffer system out of this guy. It is really, once again, the acetate part that is really the base part of this buffer system. So it's really these two things here that are acting as your buffer. And again, this is your acid part of your buffer. This is your base part of your buffer. So the main difference here is when we would take our hydrochloric acid, for example, and add it to this beaker, which again has both of those guys in there. When we do that, it will find really the base part of the buffer. I'll leave the sodium in there. And it will react together to make sodium chloride and acetic acid. And one of the things that we did talk about is one of the functions of a buffer, or one of the ways a buffer does function, is it will use up part of the buffer. but it will also make the other part of the buffer. So you're kind of using a little bit of part of it, but you are making the other part of the buffer in this case. So clearly we're just making more acetic acid here, which was in there to begin with. So that's not going to affect the pH that much. As we know, this is a neutral salt, which means it's not going to affect the pH. As we talked about last time, it's really what we don't see here, which is we have no free H pluses being formed from that HCl that's coming in, because that is a source of H plus and Cl minus. So really all that H plus gets tied up over here with the acetate, which then will go and make our acetic acid in that case. And the result of that is essentially the amount of H plus that we started with, which was this guy over here, will remain basically constant or relatively constant. And that's what's going to keep our pH relatively constant. We might have a little bit more H plus because we did make a little bit more acetic acid, which could break apart a little bit more. But the concentration of H plus in this case, again, stays relatively constant. And that is really what keeps the pH relatively constant. And again, as I talked about, you would see the pH go down a little bit if you were monitoring the pH when you added the acid, but again, not a giant jump in pH because we're really not introducing into the solution a lot of free H plus. And it's kind of the same idea when we would add our base to this buffer. The base would react with the acid part of the buffer, which is our acetic acid, and we would get a little sodium acetate and a little bit of H2O. And again, same idea. We have our acetic acid that's in there to start with. We got some H plus. We got a little bit of acetate. And in this case, when we do add that sodium hydroxide, which is a source of sodium and hydroxide, it's actually this hydroxide that's going to react with our acetic acid here, and we're just going to make water instead of allowing that OH minus to be freely floating in the solution. The result of that is what's left is actually going to make some more of the acetate in this case. And here again, there's no free OH minus entering the solution, basically. And because that OH minus stays relatively constant, that's going to keep our H plus relatively constant. And that is ultimately what's going to also keep our pH relatively constant. So really, the functionality of a buffer comes from the fact that it has both of those things. It has an acid part, it has a base part to the buffer, and that's essential for the way it functions, because when you add more acid, the base part takes care of it. 3H plus from forming. When you add more base, the acid part of the buffer takes care of it and prevents any more free OH minus from basically being formed. Any question? Then we sort of talked about the idea of buffer capacity. Again, buffers do need to be made up of sort of the proper molarity, and also sort of to handle the acid or base that you're adding. It is possible to blow through a buffer if you sort of add too strong of acid or too much acid or base to it. So there is a limit to how well a buffer could work. And that limit is, just graphically looking at it like we did. We have our acid part. We have our base part. And when we do add acid, it will react again with the base part and produce more of the acid part and use up some of the base part. And when we add base, it will use up some of the acid part and make some more of the base part. So as we talked about, if you just kind of keep adding acid or too much acid, for example, every time you add acid, you're using up some of the base part. Eventually, you can find yourself blowing through a buffer. Same thing here. If you continue to add acid or to add base, you'll blow through the acid part. That is actually, as we will talk about when we get to titrations, what happens in titrations. You actually make a buffer and then you blow right through it as you continue through your titration. Perhaps you've done titrations before, and before you know it, like there's like a, well, maybe you're not watching the pH, but you see your like indicator go like no color, and then it's like super pink, right? So there's this big kind of jump, and we'll talk about why that happens. But in certain types of titrations, you actually make a buffer as you're starting, and then towards the end, you kind of blow through the buffer. So you see this really big jump in the pH as you're going through it. So when we talk about buffers, which are really common ion sort of problems, our friend Henderson-Hasselbalch is usually the equation that we like to use a lot with buffers, and really should only be used with buffers, which is the pH is equal to the pKa plus the log of the base over the acid, where the pKa is equal to minus the log of the Ka value. Now, this equation can be used in place of an ice table, but as we saw in some examples last time, you can still do an ice table if you like to do an ice table and not use the Henderson-Hasselbalch equation. The key, though, right, is as we talked about, if you choose to do an ice table, you do want to make sure that the initial line has an initial concentration for both, say, the weak acid and its conjugate base, or the weak base and its conjugate acid. Without the initial on the right-hand side there of the arrow, you're not doing really a buffer problem. You're doing either a weak acid problem or a weak base problem. So you could still do an ice table. You could also change out the ice table and just go into the Henderson-Hasselbalch equation. We also talked about sort of the POH version of it, which is the pKb plus the log of the acid over the base. And the pKb is equal to minus the log of the Kb value. As I mentioned before, sometimes people are fond of this one for more basic situations, but to me, most of the time you're looking for pH. So why not just, cut out the middleman and just go directly into the one that's going to give you pH? So I would personally, as I said last time, kind of always just use the Henderson-Hasselbalch equation, regardless if it's acidic, basic, or neutral, works for any type of situation. I would just definitely go straight into there. One of the nice relationships that we did talk about was the pKa plus the pKb does equal 14. So that's a helpful sort of relationship that sometimes may allow you to get the pKb, pKa value. By the way, right, if I have the pKa value and I want the Ka value, that is the inverse log of the negative pKa, kind of like what we did from pH to H plus. And if you have the pKb and want the Kb value, that's like the inverse log of the negative pKb. So I could also get the Ka and Kb values if you have the pKa or pKb values given to you, very similar to those calculations. Lastly, here we talked about that we can actually use the Henderson-Hasselbalch equation to help us pick what might be a good buffer, or what might be a good thing to make a buffer out of. So a lot of times you want a pretty good amount of the base and acid part of the buffer. So if we make kind of equal amounts of both of these, that's going to give us the log of 1, and that's going to basically be 0. So typically speaking, you're looking for a weak acid or weak base that has a pKa value plus or minus 1 of your desired pH that you want to make your buffer out of. That would be the best choice to do it. Closer the better, usually. So if you got something that has a pKa value very close to the pH that you want to make, that would be your best choice to make a buffer out of. That's a lot of stuff we talked about last time, I think. Any questions on any of that there? All right. So we're going to continue on here with our buffer conversation, I think. So clearly, as we saw and as we did with our equations in our buffer solution, we would be able to essentially maintain the pH. Obviously, in a non-buffer situation, we're going to see a pretty big kind of jump in pH, and will eventually level out, but you'll see that really, really big change in pH. All right, so take a moment here. Would each of these or any of these be a good buffer? Okay, so let's take a look. So really, one of the things that we want to look at is, are the things related by basically just one H plus, right? That's the one of the things we want to look at. We also want to make sure that we got some, at least a weak acid or a weak base happening. So if we take a look at the first one here, we got a little KF and HF. We know that HF is a weak acid. KF is a salt, which is basically K plus and F minus. So these two things are related to each other by one H plus, and that is a weak acid and its conjugate base, which means, yes, there A should be a buffer system. Once again, here, the potassium is not doing much. It's just hanging out, and it's a neutral salt. When we look at B, we got KBr and HBr. So again here, this is going to be K plus and Br minus. So when we look at the difference between these two, it is an H plus. That is HBr, which is what type of acid? Is a strong acid. So could this be a buffer? This is not going to be a buffer, right? And that is because it's a strong acid. So you cannot have a buffer made up of a strong acid. Once again, if you just kind of look in the beaker, if you put all those things in, this is pretty much what you would have, H plus and Br minus. And if you put the KBr in there, you would have K plus and Br minus. You essentially have just the conjugate base part, no acid part. So will not be able to function as a buffer in this case, yeah. And lastly here, we got a little sodium carbonate and a little sodium bicarbonate. In this case, the sodiums are not important. It is really the carbonate. And over here, it is the hydrogen carbonate, right? One of those amphoteric type guys. And those two guys are related to each other. And that is comes from carbonic acid, which is definitely a weak acid. And that's the second hydrogen coming off, right? So I would say, yes, this could be a buffer. Any questions on any of those there? All right. All right, so let's talk about buffers and what happens when we do add acid or base to them. So let's just start with the first part here. So once you work on A, calculate the pH of this buffer system of 1 molar acetic acid and 1 molar sodium acetate. The Ka value here for acetic acid, 1.5 times 10 to the minus 5. So just start. Okay, so let's take a look at this and see. So they were nice enough to tell us it's a buffer solution. But I would say in a lot of problems, they won't tell you, hey, this is a buffer. So once again, you should be able to, when you look at these two things, recognize that they are related to each other. You should also be able to use the Ka value to recognize that this is a weak acid, and really the only difference here is and that this is a buffer situation. So again, a lot of problems definitely will not tell you, hey, this is a buffer. They'll just kind of give you the stuff, and you want to kind of think about that as you're looking at it. Because it is a buffer, you really do have, again, two options as to how you might want to get to the pH. You can use an ice table, and if you chose to use the ice table, in this case, you would just take the weak acid and break it apart like a kind of traditional Ka type of problem. This is again what we were talking about, that you want to make sure that you're careful here on the initial, because we do have 1 molar here, and it is vitally important for the calculation that you also put the 1 molar there. Again, if you do not do it on that side, you're really not doing the buffer problem. The rest of the table would be like normal if you chose to go the ice table approach. Probably the easier approach, if you choose not to do the ice table, is option number 2, which is really just go right into the Henderson-Hasselbalch equation. And if you go into the Henderson-Hasselbalch equation, we do need the pKa value here, which is negative log of the Ka, and that's a minus the log of 1.8 times 10 to the minus 5, which is a 4.74. That number you see 5 million times when people talk about buffers. It's everybody's favorite buffer to talk about. So the pH here would be our 4.74 plus the log of our base. Hopefully you know that that is acetic acid, which obviously would be the acid part of the buffer. This salt of the conjugate base would be our acetate. In this case, you can't really screw up since they both have the same concentration. And that would give you basically the log of 1, which is going to be 0, which means in this case, our pH will equal 4.74 to start with. Obviously, if you went through here, you would go into the Ka, you would solve for X. X would equal the H plus concentration, and then you could go into the pH, and that will get you obviously the same number here. Any questions on that part there? Okay. So let's talk about what happens when we actually do the second part of this question, which is we're going to take this exact same buffer here, and we're now going to add something to it. So I think we're going to add some acid, if I am not mistaken here. So in part B, we're going to add 0.1 molar HCl to this. For this problem only, we're just going to assume that everybody's concentration is going to be 1 liter. That's not always the case. You obviously sometimes have to take the volume into account, but just to keep this first calculation a little simpler, we're just going to assume everybody just stays at 1 liter. Basically, nobody's volume changes. Now, one of the important things to remember is when we do have a solution, and then we take another solution and we add it to it, the molarity of each of those solutions, do they stay the same or do they change? They do change, right? Because molarity is moles of solute, really, divided by liters of solution. And basically, you're changing this part of it, which means the molarity does change. The thing that doesn't change, though, is actually the top part, which is the moles of the solute in this case. So whenever you're in a situation, and buffers is a situation where this occurs, titrations that we'll talk about next is a situation where you are constantly adding volume, right? In a titration, you're just constantly adding volume to volume to volume. And in a buffer, if you have a buffer and then add more solution to it, we always need to really do our ice tables in moles because they stay the same. And then we could switch over to molarity after you do the first ice table. So typically speaking, if you're adding volume to each other, you should do that first ice table in moles. And then afterwards, it's really good practice to convert it back into molarity using the total volume at that point. So in this case, that's what we're going to do. So we're going to add to this thing 0.1 molar HCl. So we're going to take our same buffer, which is 1 molar acetic acid and 1 molar sodium acetate. It has the same, obviously, Ka value that we just used. And to this guy here, we're going to add 0.1 molar HCl. Once again, we're just going to make an assumption that everybody's basically 1 liter. So clearly, we want to think about a couple of things that are going to happen here. Since this is our buffer and this is the acid part of our buffer, and that is the base part of our buffer. When I add HCl, in this case, it's going to react with which part of the buffer? It's going to react with the base part of the buffer, which is the sodium acetate, right? Because again, we have a beaker sitting here, basically with, as I drew earlier, this situation. So when we add that HCl, which is H plus and Cl minus, as we talked about, is that H plus that's going to react with the base part, right, of our buffer in this case. And if we do that, we are going to get a reaction of HCl and sodium acetate going to do a double displacement reaction. And that will get us some acetic acid and some sodium chloride in this case. So that is the reaction that we're going to use. It's also where we're going to do our ice table from. So since we are adding these guys to each other, we do need to do this ice table in moles here because we're adding volume. So because everybody is 1 liter, that makes the moles pretty easy. So initially from our HCl, if we take 1 liter times 0.1 moles per liter, we end up with 0.1 moles of our HCl. So we'll have 0.1 moles. Our sodium acetate, we also have 1 liter of that. 1 liter times 1. 1 times 1 is 1, which will give us 1 mole. Also, always screwed up as well. Do I have any acetic acid in this case? I do. I have also 1 molar of that at 1 liter, which will give us 1 mole. So once again, if you do not have this guy right here, you are not doing a buffer problem again. So that's also very, very commonly screwed up by people as they go through this. Change here is, since it is a buffer, we know that the HCl should do what? Should we still have HCl when we're done? We should not, right? Because if it's a good working, proper working buffer, all that HCl should be gone. So instead of using X's, we actually know what the change should be in this case. It's actually going to be the moles of the HCl. So instead of using X's, we already know what it's going to be. And we can use that. We would have 0.1 mole as our change plus 0.1 mole. So that is equivalent to doing in our normal tables the x's, minus x's and plus x's, except that we already know it. By the way, couple of things, logically speaking, as we do these type of tables from here on out, this is really our limiting reagent, right? This is really our excess reagent in this case. You should always choose the smaller number, right? Because if I choose the larger number, I get what type of number? Get a negative number, which is not good, right? So I'm going to tell you this. It may not make sense now, but you will come across this debate in your head at some point. You should always take the small number. It is the right idea. Yeah? Even though your head's telling you don't take that number, should be the other number, but the other number is too big. Don't take the big number. Always take the small number, so you do not get a negative value. It will happen to you at some point when you come across a problem. You'll want to take the other number, even though in your head says, nah, you probably shouldn't do that. This is 0.9 moles at this point. By the way, we are adding on this side, which I always screw up myself. So that's 1.1, I believe, if I added that correctly, moles at this point. Any questions on this ice table? So a little bit different because we already know the change. We actually can put the change in. We do need to do it in moles because we're adding volume, and the moles will stay constant. I would say at this point in the calculation, it is a really good idea to convert back into molarity. And I will say this because in future calculations, you will need molarity to go on for the rest of the calculation. So it's just a really good idea to always convert it back to molarity. So you'll always be probably in the right units that you need. In this case, we would convert back by the total volume. So this is going to be 1 liter. In this case, we're just keeping it at 1 liter, but you may have to add. So for example, if you had 50 mils of your buffer and you added 20 mils of base, your total volume at that point at the end would be 70 milliliters, right? So we'd be dividing by 0.07 in that case. Here, just because we're going to keep it at 1 liter, that gives us 1.1 molar and 0.9 molar at this point. Now, the ice table is also very helpful because maybe you're not even sure what's going on at this point, but you could look at your ice table and see really what you have left. And what we still have left right at this point is acetic acid and sodium acetate, which is still a buffer, right? So that tells you how you could get to the pH at this point. You do have 2 options. You could do another ice table, or you can go into the Henderson-Hasselbalch equation at this point. By the way, why did I do nothing with the sodium chloride? Sodium chloride is what type of salt? It is a neutral salt, right? Which means why put numbers that you're going to use incorrectly, right? So you already know it's not going to affect anything. Might as well just leave it alone and not touch it. I'm going to choose Henderson-Hasselbalch here because it's probably going to be the easier move, but you can do a nice table if you like. So we're going to go into our pKa plus the log of the base over the acid. So now we have our same pKa as we had previously, which is our 4.74, plus the log. We want to make sure again that we get the base, which is the sodium acetate, divided by our acid, which is our 1.1. And in this particular case, looks like a 4.65. Any questions on that? Again, you would do a nice table. You would have the acetic acid and sodium acetate on both sides. That table, second table, you would do with X's and solve for X, and that would equal your H plus concentration, and then into your pH if you chose that route. Any questions on that? Yeah. So this is what I was going to say next. So let's take a look at that. This is our buffer where we started, which is 4.74, right? So the idea of a buffer is we're not going to get giant jumps in pH. So did our buffer work great here? It did work pretty good, right? Even more importantly, in these type of calculations, because I added an acid, my pH should go up or down. Should go down, and it did, right? So it went in the correct direction at least, right? So it only dropped to 4.65, but it at least went in the right direction. If I added acid like I did here and I ended up with a pH of above 4.74, I'm heading in the wrong direction, right, for what I'm doing. So again, these are things you want to think about when you are doing these calculations. Any questions on that there? All right, so why we have this here, let's just talk about the idea of buffer capacity and really what's happening. So I'm just going to steal this ice table here and then talk about what's going on, I think. So let's say that we have this exact same buffer that we made, and you were going to throw in there the 0.1 moles of the HCl like you wanted to do. So initially here, we would still have our 1 mole of acetate and our 1 mole of acetic acid. So just to illustrate in a dramatic purpose way here, you go to the shelf and you're supposed to grab the 0.1 molar HCl, but you know, whatever your day was going like that day, the 18 molar HCl seemed like the 0.1 molar bottle. So you grab the 18 molar carefully, I hope, when you grab that bottle. And that would mean that in terms of the HCl at this point, the moles would also be 1 liter. So you just added 1 liter of 18 molar. Never do this, by the way. That's going to give you 18 moles here of HCl to start with, correct? So what's going to be the limiting reagent now? Yeah, it's going to be the sodium acetate. Good luck with that buffer. It's not going to have any way of handling all that. So the change here would actually be this guy in this case, because you grabbed really the wrong concentration of it. And now the change here would be 1 mole, this 1 mole, and plus 1 mole in this case. You would end up with 17 moles of this guy. You would end up with 0 this guy, and you would end up with our 1 point, no, we end up with 2, I think, on that, moles of our acetic acid. At this point, what you would have left, right, is acetic acid and HCl. If you grab really the extreme concentration here, is that a buffer? That is not a buffer. You have a strong acid and you have a weak acid. You just made a super acidic solution at this point. So basically, the HCl is going to be the major contributor in this case, and we definitely just blew right through our buffer, right? Because we did not have enough moles of your sodium acetate in this case. So it's really the moles, right, of your buffer, of anything that's reacting. So when we don't have the right amount of moles to handle the incoming moles of acid or base, it is potential that you could blow through a buffer like this case. We would see a giant jump in pH at this point because basically just littered it with H plus all over the place. So that's why it's really important when you're sort of making buffers that you think about what you're adding, what the concentrations of what you're adding, really how many moles of everybody is going to kind of come in there, so that you make a proper buffer. Any questions on that? Yeah.
If we get two different values, we just have
You would have to use it. So this is unusual. Probably in most cases, you'll be given problems like the next one we're going to do. Like, hey, you have like, 50 mils of buffer, and then you added like 10 mils of this to it. So you'll have the volumes, and you do have to take the actual volumes into account when you're calculating, obviously, the moles of each of those things. By the way, oftentimes in problems, they'll say, hey, you have like 50 mils of your buffer, right? So that 50 mils of your buffer goes from your acid part and your base part, right? They're in there together. So you would use the 50 mils for each of the acid part and the base part to figure out the moles of each of those type things. Other questions? You would, yeah. So when you use molarity and volume, on make sure it's in liters so that you get moles and not millimoles, which might be off by a factor of 1,000 in your head. It would work as long as you understand that's what you have and you don't have moles, but most of the time you want moles. Other questions? So what we saw though in the actuality here though is our buffer really did work in this type of problem, right? And it worked pretty well. And I think as I mentioned last time, because buffers really can resist those big changes in pH, that is actually how you would, for example, if you were to make a buffer, most of the time if you just went up and grabbed everything you needed to make the buffer, when you make it and you check the pH, it most likely will not be the correct pH of what you want. And because buffers don't have these really big jumps in pH, you actually can just grab some acid or base and put some drops in, and you could dial in your buffer to the exact pH that you want before you start like your experiment and stuff like that. Because literally, like just adding drops of acid or base, you could just see the pH go up like 0.01, 0.02, 0.03, and so forth. So you could really dial them in to the exact pH that you need. Any questions on that there? All right, so let's try one here where we're not going to keep the volume the same. So we want to calculate the pH of this 0.3 molar ammonia and 0.36 molar ammonium chloride buffer. And then we want to know, after we get the pH of that, what will be the pH if we added 20 milliliters of sodium hydroxide to 80 milliliters of the buffer. So take a moment, we're looking for two answers here, before and after we add the sodium hydroxide. Probably a number you need. I'll give you a Ka value for NH4 plus. We'll go with 5.6 times 10 to the minus 10. All right. Take a few moments there, look for two answers before and after here. Okay, let's take a look and see how you're doing. So we first want to calculate the pH of this buffer. We know it's a buffer because they told us, but regardless of that, we basically have NH3 and we have NH4Cl. The NH4Cl is basically NH4 plus and Cl minus. These two guys here are related to each other by 1H plus, and that's really the buffer part of it. And NH3 is a weak base, which you could find a Kb value of 1.8 times 10 to the minus 5. And you know that that's going to be really your buffer. Because this is a buffer, we can go into our Henderson-Hasselbalch equation right off the bat to get the pH of this buffer solution. We do want the pKa value, which will be negative log of the Ka, which is negative log of 5.6 times 10 to the minus 10. Once again, though, you may be easier able to find in a table the NH3 Kb value, which would be like 1.8 times 10 to the minus 5. And you could calculate the pKb, subtract 14, and get the pKa value. You could also convert it into the Ka value and then get the pKa value. So there's a few different ways that you might be able to find the information for this. You'd probably be easier to find that kind of table if it wasn't provided for you in the actual problem. By the way, you might get a slightly different answer than what we get here, which is 9.25. You may end up with 9.26, depending on the rounding that's done. So with that, we could go in, our pH will be 9.25 plus the log. And once again, our base in this case is the NH3, right? And our acid is this guy, part of the buffer. A reminder that the acid most likely in a buffer situation should have one more H plus because it's an acid, so it has it to give, right? And the base should have one less H plus because it's going to accept an H plus. So that's the way, again, if you're not sure, you can kind of maybe figure it out as well. That means that really up on top here, we want the 0.3, which is our base part of the buffer, divided by the acid part of the buffer. And if you do that, we're going to open up this buffer here with a pH of 9.17, it looks like. Once again, if you chose to do an ice table, you also have two options. You could do like the acid ice table with the NH4 plus, creating H3O plus and NH3 and do a Ka type problem. I could also do NH3 plus some water, where it would act as a base and come on over there and give us NH4 plus and OH minus and do a Kb. Importance if you chose to do an ice table either way here, you do need a number here, you do need a number here, you do need a number here, and you do need a number here. Also on this one, though, when you solve for X, it will be the hydroxide concentration, which means you need to get the POH first and then the pH. Here, you would get the H plus concentration, from the X value at that point. So those are your two other options as to how you can get to this. This is also a basic buffers, which means some people might use that POH version of the equation as well. So that's also another option that you could get there. Lots of options, choose one that's the easiest. Maybe that's the easiest, I would think, yes. Yeah, you can kind of tell just from like, for example, the pKa value, right? It's like 9.25, so it's probably gonna be basic. Also, ammonia is there, which is a weak base, so you would probably expect this to be more of a basic buffer than something like that had like acetic acid in it that we saw earlier. We would expect that to be more like a acidic type buffer as well, looking at the pKa value for acetic acid of 4.74 as well. Yeah.
As well, but it was specific. And when we were giving the reasoning, there was a statement what you're saying now, but also the fact that you can also say because they have decreased when it was something. So in this case, it's decreasing because it's still above 9.
It's actually not decreasing in this case. This is actually the pH of the buffer to start with. So we really haven't added anything to it. We just made the buffer. So this is like we went to the shelves and threw these guys together. And now what we have sitting there, like in our beaker, is a buffer that's at 9.17. And now we're ready to add something to it. So this is sort of the starting amount of it. And again, we would expect it probably to be basic, really, because of the presence of that weak base being there. Other questions? Okay, so speaking of that, we're now ready to add the second part of the question, which is we're going to add 20 milliliters of sodium hydroxide to 80 milliliters of this buffer. So we basically have 80 milliliters of this buffer that's at 9.17. And now we're going to add 20 milliliters of 0.05 molar sodium hydroxide into here. So in this case, we are going to get a reaction that's going to occur. And we do need to do this in moles because we're definitely adding volume to volume. So this would be a situation where we do want to do it in moles. So right off the top here, we may want to just calculate some moles of each of these guys. So just kind of clear out a little bit of this here. So we really need the moles of everybody that is present. So that would be both our buffer components and also the moles of what we are adding in this case. So if we go with our moles of NH3, we're going to convert our volume of our buffer, which is 80 milliliters. So that's going to be 0.08 liters. We're going to times it by the molarity of the base part of the buffer, which is 0.3 moles per liter. and that's going to give us 0.08 times 0.3, 0.024 moles of NH3. We're going to do the same thing for our other part of the buffer, which is the moles of the NH4 plus, and that would be 0.08 liters, because again, they're both in the same beaker. They both have the same volume because they're both part of the same buffer. We would do the concentration of our NH4 plus, which is 0.36. So 0.36 times 0.08 going to give us 0.0288 moles. And lastly, we also need the moles of the sodium hydroxide that we're adding in this case. So the moles of sodium hydroxide will be we're adding 20 milliliters of this, 0.2 liters times the molarity here of our sodium hydroxide, 0.05 moles per liter. That's going to give us 0.02 times 0.05, 0.001 moles of sodium hydroxide. All right, so I'm going to move my beaker out of the way here, I think. There we go. All right. So now when we add our sodium hydroxide to this buffer, the sodium hydroxide is going to react with the acid part of the buffer or the base part of the buffer. Sodium hydroxide is a base, which means it should react with the acid part of the buffer, which in this case is our ammonium chloride. And it is going to do a little double displacement reaction here. We're actually going to get some water that's going to be formed. We're also going to get some ammonia. And for the trifecta here, we will also get some sodium chloride as well. So we'll actually get three things that are formed here because we have the chloride and the sodium coming together. Our NH4 is going to make our NH3. We're going to do this in moles. So initially here, we will have 0.001 moles of our sodium hydroxide. Our ammonium will be 0.0288, looks like 288 moles. Not going to worry about the water, right? Because that's not going to affect anything. The ammonia here, we also have moles of. So again, we do not want to forget to put this guy in there. And once again, I'm not going to worry about the sodium chloride because I already know it's a neutral salt. So again, I'm not going to do any of those things. And I am going to get rid of them as X's so nobody thinks there are X's or anything like that. So we're not going to do anything there. At this point, it is still a buffer, which means we should expect our sodium hydroxide to be completely used up. It is also the smaller number here. So that's going to be minus 0.001, minus 0.001, and plus 0.001. That will give us at equilibrium here none of our sodium hydroxide left, which is hopefully what we expect to happen. 0.0288 minus 0.001, 0.0278 moles. And lastly here, 0.024. And again, we're going to plus it on that side, 0.001, 0.025 moles. Any questions on the ice table here? It is at this point, as we talked about, that you should convert it back to molarity. So we want our total volume. So our total volume at this point, right, is we started with 80 milliliters of the buffer. We added 20 milliliters of the sodium hydroxide. That's going to give us basically 100 milliliters as our total volume when we put them all together. That needs to be converted into liters, right? 0.1 liters by dividing by 1,000. That is going to get us here 0.0278 divided by 0.1, 0.278 molar, and 0.025 divided by 0.1, which is 0.25 molar. Any questions so far? Now you get to this point and maybe you're Still not sure what's going on in terms of what I should do next. Once again, you can look at your ice table and hopefully you'll be able to recognize that you have this guy left over, you have this guy left over. These two guys are still a buffer. Yeah, they're still related to each other. Those are again the two things that you have left over. So that means we can go again into the Henderson-Hasselbalch equation, or as we talked about in the first part of the question, we could do ice tables if you'd like to. So we're going to do Henderson-Hasselbalch here. Our pH is our pKa plus the log of the base over the acid. It is the same pKa value that we used above there, which was 9.25 plus the log. Once again, we want to make sure that we get the base up on top. Our base is this guy here. That would be our base still, 0.25 divided by 0.278. All right, take two here. We'll just cut that out later. All right, 0.278 log and 9.25 in this case. There you go. 920 sounds better as well. Thank you. If you go into the Henderson-Hasselbalch equation like we did here, and you do it better than I did there, and actually put the right numbers in the right spot, you actually can go into the Henderson-Hasselbalch equation in moles. It will work out the same because on top and bottom here, the volume will cancel basically. So you could actually do it in moles if you want to. I would say it's best to convert it back to molarity because as we'll talk about with titrations, there are calculations where you do need it in molarity at that point. So it's just a really good practice to just convert it back to molarity. But truth be told, if you do go into the Henderson-Hasselbalch equation with the moles of each of those guys, you'll get the same answer as well. If you do an ice table instead of the Henderson-Hasselbalch, you would need molarity to get the sort of the correct answer and stuff like that. So it's a good idea to convert to molarity at the end of that table. And again, make sure that you sort of do it in moles so you can see what's canceling as well. Other questions on any of that there? We also see here, even with the right numbers in there, we do see that the buffer worked pretty well, right? It started at 9.17, ended at 9.20. And also the change that occurred did go in the correct direction as we added base here, sodium hydroxide. So we would expect the pH to go upwards in that case, yeah. Any questions on any of that there? Questions on buffers. So clearly you need to know what a buffer is. You need to know how a buffer functions. You need to be able to calculate the pH of a buffer by itself. You need to be able to calculate the pH of a buffer after you add acid or base to it. Any questions on any of that? Okay. Okay. Right. So this, to your earlier question, this is now what we're really comparing is, in this case, we added the base and it did go up a little bit. Yeah. Other questions? All right. So we will lay it up there, I think.